Morning, everyone. How are we doing? Questions while we wait for people to come in? Paige is asking why the last video is called Straight to Bacon. Have you heard of that game, Straight to Bacon? We were talking about that in Math 180. Did I upload it to 139 instead? Let me look into that right now. No. It's all good. Yeah, so I mean, in Math 139, we were talking about that game. You know the game where you give the name of an actor and you have to trace him or her back to Kevin Bacon through movies based on the idea of 6 degrees of separation. Right, that everybody is connected with everyone else by at most 6 people. This led to a game called Straight to Bacon, where you do the same thing but through movies. With Kevin Bacon. And in the mathematical world, there is a famous mathematician that died not too long ago called Paul Erdős. And the same thing as with Kevin Bacon, right, where you try to link back any actor to Kevin Bacon by movies in which they appeared. You can do the same with Paul Erdős. Paul Erdős published 1,525 papers in his lifetime. So if you take a mathematician and you try to link him or her back to Paul Erdős via papers that were co-authored. So, right, I mean, if you are Paul Erdős, you have an Erdős number of 0. If you are not Paul Erdős, but co-authored a paper with him, then you have an Erdős number of 1. If you are not Paul Erdős, never co-authored a paper with Paul Erdős, but co-authored a paper with somebody who co-authored a paper with Paul Erdős, then you have a degree of separation of 2, or an Erdős number of 2. Paul Erdős, 1919 to 1996, so 77. At most 77 years old. Yep. In the last 20 years of his life, he did mathematics 17 hours a day. It was, amazingly productive. Very, very smart. Yeah. Let's go back to this. We're looking for the absolute max and the absolute min. You know what to do. You know exactly what to do. You know, right, first of all, this is a polynomial, so continuous, differentiable, and so on. So you're guaranteed an absolute max and an absolute min on the closed and bounded interval. Where can these occur? These can occur at the critical points or at the endpoints of the interval. So take the derivative. Let's factor out a 6. And does this factor nicely? 6 and 4, right? X plus 6, x minus 4. So you see that critical points. Minus 6 and positive 4, both of which are in the interval. All good? So we can look at f of minus 6, plug that in. I don't know that I want to do that. F of 4 and f of 5. I'll let you plug those 3 values in. Whichever one gives you the largest one is going to be the max. Whichever one gives you the smallest one is going to be the min. There it is. Actually, we can maybe plug that in. But there it is. If you're interested in that straight to bacon game, as you might imagine, there is a website that will give you, right? I mean, you enter a name, and then it gives you either the movie that actor's name played in with Kevin Bacon, or it gives you a path leading to Kevin Bacon. It's called Oracle of Bacon.org. So if you don't have any finals to study for, you can waste some time there. Could you use a first derivative chart to find it? I mean, let's do a first derivative chart. I think we'll see what the issue is. If there's an issue, I don't know that there is. -6, 4, and 5. If you plug in 0 into the derivative, you see that it's negative. And if you plug in something bigger than 4, this is positive, that's positive, everything's positive. So right away you see that you're going to have a minimum. You have an absolute minimum occurring at 4. So that's very nice. The problem is, as Michael points out, you cannot tell which one is maximum. This one or that one. Who knows? Yep. Convinced? Questions? Well, I mean, you can certainly use a first derivative chart here as well to argue that you have an absolute minimum, but it's not necessary, right? You know the maximum and minimum are going to occur at critical points or the endpoints. So all you have to do is plug each of these in. And that's it. Yeah. Plus, plugging in is not much work if you have a calculator. You're just plugging in. So there's no thinking involved. Questions? The question could also ask for the coordinates, absolutely. Yeah. Or, in fact, the absolute maximum itself and the absolute minimum itself. In that case, you would need the values. Yeah. All right. Are there any other questions, or shall we tackle the 2004 exam? Your call. If there are no questions, well, I mean, let me start with a few questions from the exam. And if there are questions, if people do have questions, we can always tackle them. And here was one question: antiderivative of x squared, apparently. No, 2 to the x plus 4 hyperbolic sine of x. And, we never discussed the antiderivative of an exponential, but, you know what's going on. Let me ask you this. What is the derivative of 2 to the x? You know what it is. Derivative of 2 to the x. Everyone? Anyone? Nobody? Nobody yet? 2 to the x ln 2, thank you. And ln 2 is just a constant, right? So if you bring this back to the other side, 1 over ln 2 times the derivative of 2 to the x is going to be 2 to the x. And you know that derivative, that constants can be brought in or out of the derivative. So this is the same as the derivative of 1 over ln 2 times 2 to the x. What am I talking about? I'm suggesting that the antiderivative of 2 to the x, a function whose derivative is 2 to the x, is exactly that. So the antiderivative of 2 to the x is 2 to the x over ln 2. Antiderivative of hyperbolic sine is hyperbolic cos. Throw in an arbitrary constant, and you're done. You should be comfortable with antiderivatives. Absolutely. Matthew is asking for the function x to the 5. Is that times x minus 8? I mean x plus 8 squared? Find intervals of increase and decrease, I guess, if you take the derivative. Right? I mean, it's tempting to expand everything. Let's not do that. The final will be on crowd mark again. Take the derivative, right? So I mean, it's tempting to expand. Let's not give in to that temptation, and instead, let's take the derivative using the product rule. 5x to the 4 plus x to the 5 times 2 x plus 8. The point being that it's easy to factor here if you did not expand originally. You see that there's an x to the 4 that is common to both, and there's an x plus 8 that is common to both, leaving you with what? 5 times x plus 8. Here I have an x, I have a 2. That's all I have. So this is x to the 4, x plus 8, 7x plus 4. Well, Matthew, I'm not sure how you got that to. Okay, well, maybe they're the same. Who knows? No, they're not the same. Clearly, they're not the same. All right. So you see that 0 doesn't really play a role here, right? I mean, x equals 0 is a critical point, but for values less than 0 and for values bigger than 0, this is always going to be positive. So it's not, 0 is not going to be a point where the intervals change. All right, let's let's do some questions from the past final. First question is asking, to evaluate this limit. You know what to do, right? We'd like to get rid of the absolute value. And since you're taking a limit as x goes to negative infinity, you're dealing with negative numbers. Well, before we do L'Hopital's, we have to get rid of the absolute value. So get rid of the absolute value. Absolute value of y is either y or negative y, depending on whether y is bigger than 0 or y is less than 0. Like here, of course, you understand how y is less than 0. So this is going to be negative y over y, whose limit is easily seen to be negative 1. Confidence builder as the first question. Very nice. Sign you over you. You know what's happening, right? As u goes to infinity or negative infinity, this sign u doesn't approach a unique value, right? It just keeps going between negative 1 and 1. So the numerator doesn't have a limit, but the denominator goes to negative infinity. Well, Michael is suggesting that it approaches 0. Indeed it does, but we're going to have to prove that. Right? So this does not exist over infinity. Right? You don't have to write that. I'm just writing that down for your benefit. What are we going to do? How are we going to prove that? What do we know about sine? You know that sine is always between 1 and negative 1. Right? We're going to do a squeeze theorem. Sine is always between negative 1 and 1. We're going to multiply by 1 over u. Why is it positive infinity in the denominator? It's not. It doesn't matter. Right? Whether it's negative infinity or positive infinity, it's some sort of infinity. That's all that matters here. Right? And if we multiply by 1 over u, what do we get? We get sine u is between anybody? Is everybody with us? Well, I was waiting here because there's a mistake. There was a trap. Did everybody fall into the trap? What was the trap? Where's the mistake? Anyone? Exactly that. Kamal has hit the nail on the head there. You're taking a limit as u goes to negative infinity. So this 1 over u here, this is negative. And when you multiply by a negative number, the inequality reverses. Isabel had noticed it as well. Thank you. Right? This thing which looks positive is actually negative, right? Because you're going to negative infinity. So this is negative, so the inequality reverses. In other words, you get this. It doesn't affect the final answer, right? As u goes to negative infinity, this still goes to 0, and so does this. And the conclusion is the same by the squeeze theorem, but be careful, right? Inequality is preserved if you multiply by a positive number. The inequality reverses when you're multiplying by a negative number. Rachel is asking, why can't you use the fact that sine x over x goes to 1? Somebody want to address that? And user is asking the same thing. This is the limit as x goes to 0. Exactly that, right? Be careful. And that was yet another trap, right? Some people would have said equal to 1 and you're done, but it's not equal to 1. The limit as x goes to 0 of sine x over x is 1, right? And I mean, we learned that a long time ago. If you take L'Hopital's rule, this is cosine x over 1, whose limit is 1. So it's easy to see, but yeah. So it's very important. This is only true when x goes to 0. Why is 1 over u negative on the right? Well, I mean, by multiplying, I mean, I've erased it now, but when we multiply by 1 over u, the inequality reversed, right? Because 1 over u is negative. It's a, so somebody's objecting to the fact that I used L'Hopital's rule here to conclude that the limit was 1 because we actually assumed this to be 1 in order to get that the derivative of sine was actually cosine. So I'd be using a circular argument here. It's a valid point, but if you put it aside, this still has the form 0 over 0, and if you believe the derivative of sine is cos, you're good to go. Liam, it is the inequality that reverses. But the reversed inequality is actually equal to this one. Right? The reversed inequality was this, which is exactly this. Just rewritten in the usual fashion. And exactly as Yaz and Yuzra suggest, right, as n goes to infinity, this goes to 0, so this has the form of 1 to the infinity. We're going to start by taking a ln. This changes the question, so we're not going to put them equal. But in doing so, this allows us to bring the power down. And as n goes to infinity, this still goes to 0. Ln of 1 is 0. This goes to infinity, so this has the form infinity times 0, which you know to be an indeterminate form. We're going to manipulate this in order to use L'Hopital's rule, and you know the usual trick. Maybe I'll take the 2 outside. I don't need it. And we're going to rewrite n as 1 over n. In order to use L'Hopital's rule, because now you have the form 0 over 0. Absolutely. So take the derivative of the top, take the derivative of the bottom. What do we have? We have a 2 outside. Derivative of the top. Derivative of ln is 1 over times the derivative of the inside, which is minus 2 over n squared. Derivative of the bottom, minus 1 over n squared. Y is 1 over n on the bottom. That's our usual trick, Morgan, right? You know that x is the same as 1 over x. Right, because this is 1 divided by that, and you divide by a fraction, you multiply by the reciprocal. So it's our usual manipulation to get it into a L'Hopital's rule form. By doing that, we now have a 0 over 0, and we can apply L'Hopital's rule. The negatives cancel, the n squares cancel, and as n goes to infinity, this goes to 0. So the stuff in here is 2. You have a 2 outside. The whole thing is 4. What if we didn't take out the 2 and did 1 over 2n? Nothing wrong with that. Right? You could have not taken it out and done a 1 over 2n. I claim the result would be the same. As Michael suggests, it would not change. I'll invite you to do it. Convince yourself that the answer is the same. Don't forget to do a chain rule when you take the derivative of 1 over 2n. So here, this limit is 4, but that was the limit of the ln. So you have to go back and compensate by raising everything to the exponential. This is e to the 4. Absolutely. Convinced? Consider this. 1 over x minus 1 over sine x. If we blindly plug in 0, you know 1 over 0 is some sort of infinity. And sine of 0 is also 0. So it's going to be some sort of infinity minus some sort of infinity. You know infinity minus infinity to be indeterminate. Something's got to be done here. Seems like putting everything over a common denominator would be the way to go. A denominator of x sine x. And there it is. And now as x goes to 0, sine x goes to 0, x goes to 0, everything goes to 0, you have a 0 over 0. You know what to do. We're going to do L'Hopital's rule. Absolutely, thank you, Michael. Derivative of the top. Derivative of the bottom. Bottom is a product, so product rule applies. Differentiate the first one, leaving the second one fixed. Plus leave the first one fixed, differentiate the second one. We're taking a limit. So let's plug in, see what happens. Cosine of 0 is 1. 1 minus 1 is 0. Sine is 0, x is 0, everything is 0. You still have a 0 over 0. L'Hopital's rule again. Derivative of the top, negative sine. Derivative of the bottom. Here is a product, so product rule applies. All right. And when x is 0, this is 0, that is 0, but this is 2. 1 plus 1. So you have 0 over 2, which is 0. Yeah. 0 over 2, which is 0. That's it. No more L'Hopital's here. You're done. Well, this was probably the easiest one, right, of the last 3 we did. Well, I mean, user is asking, would we have questions like this on the final? Here's a problem with questions like this. If you plug this in, or if you plug this in to Wolfram Alpha, it'll give you the answer. It's too easy. Right? This is a very nice question for a sit-down exam. where you don't have any resources, but if you have the full power of the internet, what's the point? I wouldn't expect to have questions like this. I mean, maybe if we change this to a sign of kx, where k is not 0, well, you should certainly expect related rates and optimization. Absolutely. Those are essentially impossible to put into Wolfram alpha. So in that case, we're really testing U and not testing Wolfram alpha. How are we doing? But that being said, I mean, you have to be comfortable with this material. Because, vaccines coming out and we're going to be back to class probably next year. And, I mean, those of you doing Cal 3, this sort of thing comes up again. All right. Well, there are a few at the end of the 2004 exam. We'll do some. And if you have some specific questions, you can bring them next time on Friday. We can have a look at those. As t goes to infinity, what's going on here? Right? As t goes to infinity, this goes to infinity, line of infinity is infinity, so this has the form infinity minus infinity. Andre is asking if related rates question will be with variables. Why not? We'll see. Let's not worry about, well, it's still not that hard. Let's not worry about it. What I'm going to suggest is learn the material. That's all you need to do. Learn the material, everything will go very well. This has the form infinity over infinity. It's not brutal. Look, I mean, think of the last related rates question, not related rates, but last optimization question we did, where we had a cylinder inscribed in a cone. A cone of height capital H and radius capital R. Capital H and capital R, I mean, you think of them as height and radius, but they are variables. As Michael suggests. Right, so all I'm saying is, I mean, we didn't have an issue here because we thought of these variables as height and radius respectively. It wasn't a big deal, and it's not a big deal in any other case as well. So let's go back to this. Michael has given us the approach. We're going to rewrite this using properties of logarithms in this form. And as t goes to infinity, this stuff in here has the form infinity over infinity. You know what to do. We could have evaluated this separately and then taken the ln, or perhaps factor out a t squared from the denominator to cancel with the t squared on top. As t goes to infinity, 7 over t squared goes to 0. So this stuff in the bracket goes to 3, and we get ln 3. As Sean predicted. You could, that's interesting. Annie suggests why not take E right here. Well, at the start, you have to be careful, right? Because it's not going to be e to the ln 3t minus e to the ln t squared plus 7, right? You really have to do this first step first, and then you could take the exponential of both sides, meaning just evaluate this limit, maybe using L'Hopital's rule, and then take ln of the whole thing. That's fine too, right? An alternate approach here would have been to take a step and say, I'm going to evaluate the inside. Separately, as a separate step, find a limit of 3 using L'Hopital's rule once or twice, and then say that this is ln 3. In other words, you can take the limit inside because you know ln is a continuous function. So the limit of the ln is the ln of the limit. Well, first of all, ln x is not 1 over x, right? The derivative of ln x is 1 over x, first of all. Secondly, you cannot take the derivative of the function. Right? You don't have 0 over 0 here. X approaches 8, yes. Right? You don't have this thing right here, doesn't have the form 0 over 0 or infinity over infinity. It's ln of an indeterminate form. So either you set it, either you look at this separately. This has the form infinity over infinity. So you can apply L'Hopital's rule here, but you cannot apply L'Hopital's rule to the ln of that expression. All right, let's move on to this. And I think everybody has observed that this has the form 0 over 0. What are you going to do? You know what to do, right? I mean, it's tempting to use L'Hopital's rule again, but you know, you've done a few of these, and I think you know that L'Hopital's rule will get you stuck, will it? I suspect L'Hopital's rule would get you stuck in one of these infinite loops. So let's not. When x is 8, you get 8 squared minus 8 squared. I think you get 0 over 0. So instead of using L'Hopital's rule, because you know we have other tricks, you could use L'Hopital's rule. I claim, and I'll invite you to try it, I claim you're going to get stuck in one of these infinite loops where you get 0 over 0 all the time. And you want to stay away from those. Usually happens when you have a square root involved. Not all the time. Well, I mean, I'm not 100% sure. I'm not 100% sure, so why don't we do it? Let's do it. Let's do L'Hopital's rule, see what happens. It's just a feeling I had. The derivative of this is 1 over square root. Derivative of this, there's a 2 there. Derivative of this, 1 over 2 square root of 2x times the derivative of the inside, derivative of the denominator, 2x on the side. Absolutely. But now you're thinking to yourself, well, wait a minute. This is, okay. So this is 16 minus 8 is 8, so that's not 0, that's not an issue. And here you get 1 over 2 root 16 minus, well, first these two things cancel. So 1 over root 16 minus 1 over root 16, that's 0. And you're done. All right, I was reading way too much into that. I expected an infinite loop. Didn't happen. Perfect. But for completeness, what would you have done if it had been one of those infinite loops? How would you have treated this without using L'Hopital's rule? Could you treat this without L'Hopital's rule? Multiply by the conjugate. Very nice. Right, so it's an important trick. Here it wasn't necessary, as you've pointed out, but it could have been. Do we have time for one more question? Well, maybe a good place to end. Matt got minus 1 over 64. Interesting. Let's have a look at that. If instead we multiply by the conjugate, square root of x plus 8 plus that over itself, let's just do that and we'll end with this, see what happens, right? You know what happens when you multiply by the conjugate. It gets rid of these square roots. We get an x plus 8 minus 2x. We'll leave the denominator factor, right? This x squared minus 8x is really x times x minus 8. And then we have this business. And this is 8 minus x. which is going to cancel out with that. So what happened here? What's going on? You're right that you get a -1. We have seemingly made a terrible mistake. Does anybody see where the mistake is? So first of all, here your numerator is 8 minus x. And this cancel to leave you with a -1. And so your answer is -1 over 8 times 16 plus 16. So that's 4 plus 4 is 8. So -1 over 64. What have we done? The derivative of this Where's the mistake? Anybody see the mistake? The numerator is not 0. Because of this 2. Exactly. Numerator is not 0. Thank you. This is 1 over 2 root 16. So this is actually 1 over 8. And this is one over root 16, which is 1 over 4. Here we go. And this is, the denominator is 8. Here we go. So this is -1 over 8, which is -1 over 64. Thank you. Absolutely. Absolutely. But it's nice to be able to do it 2 ways and therefore see what the mistake is. Exactly. Well done. Well done. So a good place to end, because I mean the next questions have to do with derivative. We will tackle those on Friday, unless you come armed with questions that you want us to do instead. We can do those first and move on afterwards. Thank you all for coming, folks. I will see you on Friday.